So if you have not done so, please make sure that you have turned in your assignment for our last lesson 6.2 over sound and sound waves. And before you get into taking notes on this lesson, please make sure that you've watched this video. It's almost 8 minutes long, but it does a nice job kind of brushing over all these different topics that we're going to be going over in our notes. That hopefully will make it just easier and more visual for you to learn it. So as we get into this, it's there. So as we get into Unit 7, then we're trying to make a connection from what we learned in Unit 6, which was the mechanical waves and the sound waves. And we will see that there's a lot of similarities between mechanical waves, sound waves, light waves, and there are some distinct differences. But it's just, excuse me, the idea of getting you to connect your thinking from one to the next and being able to predict what is going to be true about both of them. So this particular question, when we get started, says sound and light both travel by waves. In order to hear sounds or see light, waves must travel from one place to another and enter either your ears or your eyes. How do you think these waves travel? Well, when we look at our three different options, the correct answer would be A. And what that's saying is when we talk about sounds and mechanical waves, we talked about the medium, the material that the matter, the energy is going to travel through. And it said, such as sound waves, the least dense, the more spread out the particles in the material is, the harder sound has to travel, right? It has a more difficult time. So when we compact those materials, when the medium is thicker, such as the idea of iron, sound will travel much further, much quicker. Well, we're going to see there's a difference when it comes to light, but both of them need matter. They need a medium to be able to travel through. So as we get into our notes then, and we start delving into Unit 7, Lesson 1, we often want to know, well, what is this stuff, right? What is light? And we know that light is around us. We go outside during the day, we have the sun. If, we have a pretty decent moon, then we have the moon outside at night and we have light. We have our light switches. We flip it on and suddenly there's light. And when the electricity goes out, we can grab our cell phones and push the power button and that screen will light up. That'll give us light. And then if it's really dark especially for an extended period of time, then on our cell phones, we can slide up and turn on our flashlight, or we can find a flashlight. So light is something that we are so used to using and having there, but we don't necessarily think of what it is. Now, as I told you, between sound and light, there are so many things that are the same, but there are some very distinct differences. Sound is when we apply energy into a matter and it carries energy forth. Well, when I look at light, it tells us at the very beginning of our notes, once again, assignments coming up. So please mark up your book, take your notes, pay attention so that you can make this easier for yourself. But it says that light is neither matter nor energy. It's simply a type of wave. Well, what type of wave is it then? Well, these are waves that are called electromagnetic radiation that it allows us to see. Now, when we look at the idea of electromagnetic radiation, that gets into some sciences and terms that become quite challenging, especially for our level as sixth graders, where we're really delving into science for the first time. And I don't expect you to understand what electromagnetic radiation is. Just know that that's what the definition of light is, right? So when we start seeing light and you watch the video, it talked about how what we see, excuse me, is a very small portion of all the different types of electromagnetic radiation or light waves that are out there. So we often refer to that specific realm that we can see as light. And then we have, the sub levels of infrared and microwaves, which are lower than the light that we can actually see. And then we have the higher ones, which we often refer to as like ultraviolet, which we can't see also. So we have this huge spectrum of light of these electromagnetic waves. But light is truly just the part that you and I can see. So it's the idea that energy is carried from some kind of source, right? So we have radiant energy being created from some type of source, and it's a byproduct. It's what it creates that we call light, and it's the portion which we can see. And once again, there are many different types of these electromagnetic waves. The waves that we can and cannot see are very wide and far between. We're kind of in the middle group of what we can see, and that's what the book is showing you here. This is what we refer to as visible light. There are some who have um, brighter or broader frequencies, there we go, that we can't see, and then more compacted frequencies that we can't see either. So the human eye is designed to only see certain types of visible light. And I believe on the video it even mentions that there are some animals out there that they can see different levels a little higher and a little lower than what you and I can see. But it's just because that's the way they created. Does that mean that there are a variety of lights that we cannot see? Yeah. And for some people, that gets a little weird. They're like, if there's light around us, why can't we see it? Because that's the way your eyes are designed, right? And that's okay. So notice we have all sorts of tools that we use today that we have figured out that these lights exist and we use them for the. So when we start looking at the comparison, what they do have in common, notice it says that a light wave, just like mechanical waves. It's not saying it is mechanical waves, but it's saying that there are similarities between the mechanical waves, such as the water waves or the sound waves, and the light waves. And what that is when I measure them, when I have a tool that is able to see the different light waves or electromagnetic waves, then I can see two different parts that are still the same. So there's actually more than just two parts, but we focus in on wavelength and frequency. So notice that there's still crests and there's still troughs, right? Wavelengths and wave heights. But we want to focus in on the wavelength and frequency, and we'll apply that in just a moment on how they're very different when it comes to light waves compared to water waves or sound waves. But once again, a wavelength is just the distance from one part of a wave to the very next wave's part that is the same. So it could be from crest to crest, as we looked at when it came to like the water waves when we labeled. Or it could be in this example from trough to trough. It is that distance from one to the next. We also look at frequency, and frequency, once again, is how many there are over a given period of time, right? So we count them. When it comes to the ocean, it's a little easier to be able to do because they come a little bit slower, able to usually, count them. And we can see like a bob or a buoy going up and down over so many times. And we can use a stopwatch. When it comes to light waves, not so much, right? But it's still the idea that we can measure them. And because they do happen so fast, then we have what's called a nanometer. And that's really beyond what we need to understand in sixth grade. I'm just telling you what that word is. It's nanometer, and it's how we actually measure light waves. So when we start looking at this relationship, then we can see that we have wavelengths, we have frequency. However, way we count them and the outcome is very different between mechanical waves such as water and sound compared to light. So what the book tells us is when it comes to a water wave, right, which we started with in our previous unit, the high amplitude or the wave height it means it has a lot more energy. And we talked about how that energy is blowing from the wind is moving the waves, and the closer I get to the shoreline, then that energy is going to hit against something solid and push the waves up. So the higher up they come, then the more impact they have. The closer you are to the edge of the shoreline, if you're playing at the beach, the more difficult it is for you to stand because the higher the wave, the more energy is. It's slamming against you and it's going to be throwing you around a little bit. And then we also took that into the idea of tsunamis, right? So tsunamis, underground earthquakes or erupting volcanoes cause these giant waves bigger than you and I could even imagine. Um, So they're going to cause all sorts of destruction because there's a huge amplitude or high wave height. When it comes to electromagnetic waves, or what we group as light waves, then we look at our frequency and not the amplitude. So the more wave crests and wave troughs that we have, the more compacted the energy is that we are able to measure. Right? Then the more impact, the more light, the more brightness there is, the more we're able to see it. So when we start talking about, what causes these waves that we can't see and these waves that are ultraviolet waves and things like that, it's because of the frequencies, not because of the amplitude or the wave height. It's the frequency. How many waves do we have? So we have these very low, slow waves, which are going to be like our microwave. That's how we were able to create this device called a microwave. We use these lower waved electromagnetic light waves to heat our food, basically. It's also our radio waves. They're very low frequency. They don't travel nearly as fast as different types of rays, like gamma rays. X-rays travel at a faster. We can't see those type of things. Ultraviolet, we can't see. Um, so they're going to be traveling, have a higher frequency, and therefore they're going to have a greater energy, a more impact on what it is that they're hitting. So that takes us into the light that we can see. And when we talk about the light that we can see, then one of the things that we have to talk about is brightness. And brightness, as the book tells us, it's really a person's perception of how intense light is. Now, it's not saying that there aren't lights that are brighter than others, but for some of us, we have more sensitive eyes than other people do. It is often people that have lighter colored eyes that they are more sensitive to sunlight. But some people, such in my case, where I had eye surgery done several years ago, it caused my eyes to be much more sensitive. That's why if we go outside at recess, I have my sunglasses on because my eyes are very sensitive to direct sunlight, and it usually will end up causing me a headache. But sometimes brightness is about a person's perception. Other times it's dealing with because the amount of energy that is being given off, or it could be how close a light is to us. So, one example of the amount of energy. So, for you, you're in your room and you feel like your lights are too bright. So, you're asking your mom and dad to put in softer lights. So, we have soft lights and we have lower wattage light bulbs, right? So you may want a 30. It gives you a nice soft dim light, but you'll still be able to see. But for some of you, it's like that's way too dark in my room. I really need more light, and you want a 100-watt light bulb. So on a wattage on a light bulb, the lower the number, the softer the light is, the less energy or amps that can be released into that particular light bulb at any given moment. The higher the number, the brighter a light's going to be. And that is truly not somebody's perception. That is truly, there's more energy, there's more amps or watts going into that light bulb. So therefore, it's going to be brighter. And then sometimes, when you are close to someone outside, maybe playing tag, and you have a flashlight and you're further away and you can barely see their flashlight, well, you know they're coming. But if someone sneaks up on you, flashes it in your eyes because they're closer, wow, that brightness is so much more harmful to your eyes because you're like, ow, I didn't feel good. So when we have these distances or these amount of lights, then it could be the energy, right? The light from a flashlight, it's good, it's strong. You poke it into your eyeball when it's really dark outside, it's going to hurt. But compare that to the sun, wow, there's a whole lot more energy, right? And since there is more energy, it's definitely much brighter than a flashlight could possibly be. So that's not necessarily the idea of the amount of energy is, someone's perception. There really is more energy there. In the same way, if you are out at night, especially on a new moon phase when there isn't a big bright moon in the sky and you can see stars, some stars seem really bright. It's not because they're bigger, it's because they're actually closer. And the closer they are, the brighter and bigger they seem to be, even though they're still millions of miles away. And then there are some stars you can barely see a little itty bitty speck of light because they're so much further away. Some of those itty bitty teeny tiny specks of stars out in space are actually much bigger than the ones that are closer to us. But because they're so much further away, they seem so much smaller. In the same way, when we talk about, light and sensitivity, right? We talk about how close something is. Well, once again, if it's really close to us, then it's very bright. And if it's further out, then it's not as bright. But some of us just have sensitivity to light. I know that, once again, when I go outside in direct sunlight, I'm constantly squinting if I don't have my sunglasses, but generally I'm going to have my sunglasses on. But when I drive at night, it's the same thing. For some people with headlights coming towards them, that doesn't bother them. The intensity of the headlights isn't a problem. But for me, I really have to squint because it does indeed hurt my eyes. And that is just a perception. That's the way my eyes interpret the light. Some people interpret as, not as bright and difficult to see, and other people do. So when we talk about brightness, that's one of those things that, you know, it's a perception, just connecting to the idea of the mechanical waves. When we had sound, we said loudness is a perception. It's not necessarily, oh yeah, that's loud. It's, well, I interpret that. So how exactly does the light turn? So when we talk about that question, well, how does light get to us then? Right? Well, then from the sun is this giant exploding ball of gases and creation of light as well as heat. And it takes a little bit of time for it to get to us, right? If you would call somebody on the phone, but they can't hear you for about almost 10 minutes, then that's going to be really weird and difficult to have a conversation. But because light is constantly being emitted from the sun, we don't notice that it's taking that long to get to us. So if the sun would happen to go out, hypothetically, then we wouldn't be aware that the sun went out for almost 10 minutes. But once it's gone, then sheer panic is going to happen, right? So when we talk about the difference between light traveling here on Earth compared to traveling to Earth, then we talk about space. And once again, space is this giant vacuum. It is void of matter. It is void of material for the most part. Yes, we have celestial bodies. We have planets. We have stars. We have moons. We have asteroids. But when you're traveling out in space, and I tried to bring this up when we were talking about astronomy, we have all sorts of pictures in our books and online, and we can see all the different planets in this nice specific order out in space. But when we actually would go out into space, we could go hundreds of thousands of miles without seeing any celestial body out there at all. We could travel for days and months and even years before we would run into some other celestial body like a planet or a large asteroid or a moon even. So we don't have a lot of stuff out there. And one of the main things that doesn't have is air. And so when we start talking about light traveling from the sun and taking nearly 10 minutes to get to us, that's still pretty quick. And we don't think about that as being quick, but that is really quick. So when we talk about why is it able to go through a vacuum, because there's nothing hindering it. And that's the difference between sound and light. Sound must have air, it must have particles, it must have that medium to carry the energy forward for it to travel. Light is just the opposite. The more matter, the more material there is, the less light gets through. So when there isn't any, such as in the vacuum of space, light can travel as quickly as possible without any hindrance, without anything to slow it down. Excuse me. So once again, that idea of a vacuum is the absence of matter, absence of material. Right now, it's not saying it's completely empty because we know, once again, we have moons and planets and asteroids and stars out there. But what we're talking about is all those gases and things that build up our air. It's not out there in space. So light can travel super fast. So when we look at the idea of, well, how fast does it travel? Right? So electromagnetic waves in a vacuum going from the sun to the earth, for example, travel at 300,000 kilometers per second. That is further than you and I can possibly imagine in our minds because we've never traveled that far, let alone in a second, right? So it's difficult for us to understand. But one of the things that we talk about is that when we're talking about air, and even though air will slow down light waves and it can't travel nearly as fast, it's still that light can travel so much quicker than sound, right? And for example, they tell us, if we look at the idea of lightning and thunder, right? Unless lightning is striking right next to you, you're not going to hear the thunder and lightning at the same time. You're going to see the light first. You'll see the strike. And then the sound has to travel through all of that material, all of that air to get to us. So it slows it down. The light is still so much faster, 900,000 times faster than sound is, right? So when you see lightning, then that's why you can usually count, because we know how fast sound will travel to figure out how far away a storm is. So if you count like 3 seconds, then they say, well, then the storm is about 3 miles away from you. So you'll see that light because it travels so fast before you ever hear the sound, which still travels fast, just not nearly as fast as light does. So what I was trying to get to a moment ago is the idea of the compacted materials and how that affects us. So this will be where we finish today's notes, and then we'll pick up again tomorrow. But the idea is that when we have compacted material, then light struggles even more to travel through things. So when we have an open vacuum, right, there's no air, there's no matter and material for light to travel through. It goes 300 kilometers per second, or 300,000, excuse me, kilometers per second. And then notice with glass, it travels at 193,000 kilometers per second. Now that's still fast, right? When I turn on a light and there's open glass, we can't see it being delayed, but it is being delayed, right? And it makes it just a little bit slower. So what we're saying in comparison between sound waves, right, those mechanical waves, and then these electromagnetic waves, what we refer to as light waves, then the less particles that are in the material that it's traveling through or the absence of material, the faster light can travel. In opposite to that, with sound, the more compacted a material is, the faster that sound can travel. So we talk about air and how in air, sound can only travel at 300 meters per second. That's because the material, the matter in the air, the particles are all spread out. But when I talk about steel, tightly compressed particles that are holding the metal together, it travels at 6,000 meters per second. That's much quicker, right? So we're really talking about opposites of one another when it comes to how fast they can travel. Sound, the thicker the material, the quicker the sound's going to travel. However, with light, as we'll see in tomorrow's lesson, the more compacted the material, the more difficult it is for light to travel. So if there is any time left in today's class, then please go ahead and continue to work on IXL or something else. If not, then we will continue this tomorrow.